Okay guys, in this video we are going to continue our discussion of chemical kinetics, and in this topic we're going to discuss what are known as integrated rate laws. So previously we have looked at rate laws that have this format, right? We've looked at expressing the rate in terms of the time derivative of some reactant or product. In this case, we're doing it for a reactant. And then in the last video, we looked at how to express the rate in terms of concentrations directly through the experimentally determined rate law. And for a reaction like this would be the generic form for the rate law, and you'd have to do some experiments to determine x and the rate constant. This is a mathematical equation known as a differential equation, and you can solve the differential equation by finding the function a as a function of t that satisfies this differential equation. And so that's what we're going to play around with in this video. We are going to look at zeroth order, first order, and second order kinetics. We'll solve the differential equations to find the concentration of A as an explicit function of time, and then we will analyze those we'll analyze those solutions, those integrated rate laws, in different ways, including graphically, which is quite important, quite an important aspect of what we'll be learning about. For each of the different kinetics that we will study, there's another quantity that's of interest to us, something called the half-life. The definition of the half-life is the time that is required for the reactant concentration to equal 1/2 of its initial value. So this is the formal definition of the half-life. And for each of the types of integrated rate laws that we discuss, we can derive the half-life formula, that is the formula for T, for T1/2, in terms of the rate constant and the initial concentration of the species. So let's get into that, and let's do this for zeroth order kinetics. So we're going to take a reaction of the form like this, where the experimentalist tells us that the rate, which I'm going to write as minus dA dt, equals Kr times the concentration of A to the 0 power. So this is a zeroth order rate law on the right hand side. And so what we're going to be doing is solving this differential equation for A as a function of time. And so how we do that is we rearrange the differential equation. So we can write it like so. And then it's easy. From here, we just integrate both sides. We'll integrate from the initial concentration of species A to the final concentration, and then we'll integrate the right-hand side from 0 to some time t. Note that the rate constant doesn't depend on time, and it comes outside of the integral. And so the left-hand side gives us A minus A0. The right-hand side of the equation is going to give us Kr times T minus 0, which is just minus KRT. And so rearranging it, we get this expression here for the concentration of species A as a function of time. We see that it's a linearly decreasing function. So if you were to plot A versus time, the intercept would be A0, and then it would decrease here, and the slope would be equal to minus Kr. So for zeroth order kinetics, what you can do is monitor concentration versus time. So you get these data points, and then you plot the data, concentration versus time, do a linear fit. The slope gives you minus the rate constant. What about the half-life for zeroth order kinetics? Well, at the half-life, A will equal A0 over 2, okay, which is going to be equal to A0 minus K times the half-life time. So at T equals T1 half, A equals A0. So that's the definition of the half-life. You can then rearrange and solve for T1 half. And for zeroth order kinetics, what you find is that the half-life time increases with the concentration of A0. So the more you start with, the longer the half-life time. Conversely, the larger the rate constant, the shorter the half-life time. In general, large rate constants mean fast reactions, and small rate constants mean slow reactions. Let me illustrate the half-life on this graph. So here's our initial value of A0. The first half-life interval will be the time it takes for this concentration to decrease to 1/2 its initial value. So we go all the way over here, bring it down. So this interval, that's our first half-life time interval. Notice that now, since the initial concentration is down to here, we could imagine going one more half-life interval. And so half that concentration would be here. What has happened, you see that the time it takes to get to 1/2 of the 1/2 concentration, you see that that time interval has decreased. So this is the second time interval. And it's decreased because we started out here. And so it took proportionally less time to get to the half-life. You could repeat that again. So that would be the next half-life time interval, and so on. And it just keeps getting short. The half-life time interval just keeps getting shorter and shorter. Eventually, in a zeroth order reaction, the concentration of the reactant is going to get down to 0, and that's when the reaction stops. The next slide here summarizes the important aspects of the zeroth order kinetics. So here's the differential equation that we were working with. Here's the solution. You can also derive, and it's not very difficult, you can derive the solution for the product concentration. You see that the reactant concentration decreases linearly. The product concentration is going to increase linearly so long as T is less than this end time. So that's the time here, A0 over KR. This is the time where the reaction finishes. I've shown you how to deduce from the rate law what the units of the rate constant are, and so those are given here, right? Since the rate is has units of moles per liter per second, the rate constant also has units of moles per liter per second. I've already discussed the graphical aspect and derived the half-life formula. And so you really need to know all of these results here, and then you need to know this graphical form as well, which I've already drawn for you over here on the video camera. What they're showing you in this graph is different values of the rate constant. So a large rate constant, you see the line has a very steep slope. For a slower reaction, the line has will have a smaller rate constant and will have a more gentle slope. Well, let's do the same thing, but we'll do it next for first order chemical kinetics. So it's the same generic reaction. This time, however, the experimentalist tells us that the rate is first order kinetics. So we're told, the experimentalist is telling us this. And so now we're gonna solve. It's a different differential equation, and it has a different solution. And so we'll find that. What we'll do is we'll put the parts that depend on A on one side,
of the equation, and we'll part the parts that depend upon t on the other side, okay, which is just the dt. And so now what we'll do is we'll integrate both sides. We'll integrate the concentration from A0 to A, and we'll integrate the time from 0 to t. This integral is the same as what we had before, but this one is different from what we had before. But we've actually seen this type of integral before. dA over A, very similar to dV over V from thermodynamics, and the result is the same. You can break up the natural log. So sometimes you see, I'm going to go ahead and write it explicitly. So sometimes you will see this form for the first law, for the first order kinetics integrated rate law. However, you can go another route. You can exponentiate both sides, and I'm just going to put it down here. You can also write it like this. Here, this is the part that I like because it highlights the exponential decay of the reactant, which is the hallmark of first order kinetics. I like to call this the linear form of the first order rate law. And the reason I call it the linear form is that if you take, well, let's start with the exponential form. If you plot A versus T, here's your initial concentration, A0, it decreases exponentially. And that's the exponential decay here in this form. The linear form is going to look just like that. It's going to look linear. You'll start with some natural log of A0 at time t equals 0, and then it's going to decrease linearly with slope equal to minus kr. So what you can do is you can measure concentration versus time. So you measure concentration versus time, then plot the data as the natural log of A versus time. Make a graph like this. Fit the data to a line. The slope of the line equals minus the rate constant. Okay, and so that's how you can measure rate constants for first order kinetics. The half-life formula. Let's go ahead and take, it doesn't really matter which form. I'm going to go ahead and use this form here. A will equal A0 over 2 when the time equals the half-life time. So at the half-life time, the concentration of the reactant equals half the initial concentration. You see that those cancel. So you get 1/2 e to the minus kRt to the 1/2. Take the natural log of both sides. Natural log of 1/2 equals minus kRt 1/2. Rearrange, you get that the half-life time equals the natural log of 2 over kr. And what I'll point out here is that the half-life time for first order kinetics, it's inversely proportional to the rate constant, just like zeroth order kinetics. So the larger the rate constant, the smaller the half-life time. The faster the reaction, the shorter the half-life time. But it does not depend upon the initial concentration of the reactant. So it doesn't really matter how much you start with, the half-life interval is going to be the same. And you can illustrate that for an exponential curve, assuming I've drawn something that's pretty close to exponential. Take the half-life, so we'll take half the initial concentration, we'll walk over here. So this is now our first half-life interval. Let's take half of that, walk over here. Lo and behold, it's the same, roughly the same, based upon my artwork, roughly the same time interval. Do it again, come down, it should be the same. So the half-life interval for successive intervals is the same for first order kinetics, and that's because the half-life doesn't depend upon the initial concentration. let's look up the cleaned up results here. So here I've got all of the important formulas at the top. If you want, you can also derive for yourself how the product concentration changes. Species A decreases exponentially. You're going to find that the product increases exponentially. The rate constant from the rate law has units of reciprocal seconds. And I've already discussed the linear form of the natural log of t graph and the half-life formula. And so these are all very important features. Here's some graphics. Okay, so this is illustrating the effect of the rate constant. If you have a large rate constant, you're going to decay exponentially faster than you will if you have a small rate constant. Here it looks like we have a they want us, this would be a graphical problem. They give us some data for this gas phase reaction. They're plotting the pressure as a function of, or they've measured the pressure of the system as a function, or this would be the pressure of, the partial pressure of azomethane. Okay, so they have the partial pressure of this reactant as a function of time, confirm that it's first order, and then find the rate constant and the half-life. So you take the data, you plot it as natural log pressure versus T. The slope is going to give you the rate constant. The slope is minus Kr. And then to get the half-life, you would use this formula here. You take natural log of 2 divided by that rate constant, and it would give you the half-life time. Well, let's move on to the next type of kinetics, second-order kinetics, and find the integrated rate law for second-order kinetics. So again, the same generic reaction. This time the rate is, from the experimentalist, they tell us it is a second-order reaction. So a different differential equation that will have a different solution. Same approach. Put all of the parts that depend upon A on one side of the reaction, on one side of the equation, and the parts that depend upon time on the other part. Then we're going to integrate both sides. This integral is the same as the previous two cases. This is where it's different. And so you're going to wind up with, for this one, it'll be 1 minus A minus negative 1 over A0 equal to minus KRT. Let's go ahead and cancel the minus signs. And that's going to give us an integrated rate law that looks like this. Not very pretty, but that's what it is. If you plot 1 over A, the concentration of the reactant versus T, what you'll find is an upward sloping graph where the slope is equal to plus Kr, and the intercept is 1 over A0. So for second order kinetics, you would design a different graph. You'd get your data, you'd fit it to a straight line, and then the slope would be equal to the rate constant. The half-life, same procedure. 1 over A would be equal to 2 over A0 at the half-life time. So then you just solve for the half-life time. You'll get T1 half equals 1 over Kr A0. Okay. Again, it is inversely proportional to the rate constant. So the larger the rate constant, the shorter the half-life time, the faster the reaction. This time, it does depend upon the initial concentration, but you see that it's inversely proportional to the initial concentration. So the larger the reactant's initial concentration, the longer the half-life time. Okay, so that's different for second order kinetics compared to first order and compared to zeroth order kinetics. It's in the denominator now. Here is the cleaned up slide with all of the facts presented. We've got the differential rate law, the integrated rate law, which they've rearranged algebraically compared to what I've shown you. I prefer my format here because this one tells me that it's linear, but this is a nice form as well. You can also find the concentration of the product as well. You have to do a different integral to get that. Let's see, did I give the correct units here? Yes, it should be liters per mole per second. That would be the units of the rate constant. Like I said, this one gives you the linear graph. Here's the half-life formula. Here is a graphic showing you second order kinetics. So here we've got two different rate constants. Again, the larger the rate constant, the faster the reaction goes. What they're comparing against with these gray curves are the integrated rate law for zeroth order for first order kinetics, where the initial rates are the same. So you see that the slopes of the two curves, the two pairs of curves, are the same at the beginning of the reaction. And what they're trying to highlight is how the second order kinetics kind of drags on. So it's like the reactions for second order kinetics, they become slower and slower in a sense as time gets larger and larger compared to the first order kinetics. Anyway. Here's another example. This is a different type of reaction, one that I won't derive the equations for. This would be for we'll call this a bimolecular type of reaction later, but we've got two reactants, but the reaction is first order in each, but second order overall. So here's the generic rate law. You see that it's first order in species A, first order in species B. If you add those orders together, it would be second order overall. Here's, I won't derive it, but here is the integrated rate law for that case where you can vary the concentration of A and B, the initial concentration of A and B independently. There's a special case when the two concentrations are the same and the equation separates into two second order equations. Here in this problem, it's just making use of the integrated rate law. So consider a second order reaction that's carried out in solution. They give us the initial concentrations A0 and B0. After 1 hour, the concentration of B has fallen to that value. Calculate the concentration of A and the rate constant. So looking at this relationship here, let's just write out what they've given us. So in this problem, they've given us both A0 and B0. They've given us the time it takes, and then they've given us the concentration of species B at that time. What they want to know is what is the concentration of species A, which we can get from the stoichiometry, right? It's a one-to-one relationship, so you can deduce what the concentration of species A is from the stoichiometry. It'll be, the concentration of A will be equal to A0 minus the amount of species B that has reacted, which will be B0 minus B. So you get that number as well. So once you know all of these numbers, you then just need to algebraically solve for the rate constant. I'm going to go ahead and stop this video right here, and we'll pick up with equilibrium reactions in the next one.